All right, well, welcome to our next video. This video is on the rate of heat transfer, and another name for the rate of heat transfer is thermal power. But before we get to rate of heat transfer and thermal power, going to take a quick look at what it means to be in steady state. So steady state is when at a particular point in a system, the properties aren't changing with respect to time. So if I were to write the first law, we would write it, in the past we've been writing it like this. We've been saying, well, the internal energy, initial plus kinetic energy, initial plus potential energy, initial. Notice I'm doing this in total terms. All right, well, I hit pause and finished writing out the equation. I don't want you to write this down, but I want you to look at it, and then we're going to simplify it. So we've got the initial energies, and then heat in, work on, heat out, work by, mass in, mass out, and then we're left with the final energy. Well, when we have steady state, what we do is we say if the energy isn't changing from before to after, that would mean that the final energy on the right and the initial energy on the left would be the same value. So that's what steady state means, is that those go away. If they're the same on both sides of an equation, we can eliminate them. All right, I'm going to go ahead and rewrite the equation, and I'll hit pause to do that, and then once I get it done, you can join me and in writing it in your notes. So I've gone ahead and typed the equation, Q in plus W on minus Q out minus W by plus mass in times U in minus mass out times U out. Now you'll remember from our one of our last videos the difference between a capital Q, meaning total, capital W is total, so this would be like BTUs or joules, capital Q, capital W, and then a mass, which would be like in pounds, times a little u, that'd be like BTUs per pound, pounds divided by BTUs per pound, or times BTUs per pound, cancels out the pounds, and we have BTUs, 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 BTUs. I went ahead and for our conversation here have eliminated the potential energy and kinetic energy. And the reason we get to do that in almost all thermosystems is because it's so small compared to the internal energy. And in fact, the internal energy would be better written with as the enthalpy. I think I'm going to go in and change my equation here. When you write this down, instead of putting U, let's put H in and H out for the reasons that we talked about in the enthalpy video. Well, if we're going to go to rate of heat transfer, we're going to take everything here and divide it by time. And if we divide it by time, all we do is we put a dot above the Q's and the W's and the mass. And when we do that, let's see, if that's divided by time, so BTUs per hour, it'd be Q dot, BTUs per hour would be W dot. Let's take a look at mass flow rate. We'd have pounds mass per hour times little h is BTUs per pound mass. I don't know why my video keeps freezing on me. And the pounds mass would cancel. We'd have BTUs per hour and BTUs per hour. So this is going to get us to the steady state first law. Steady state means the initial and final go away. The first law, we'll go ahead and get we will neglect potential and kinetic energy for now. We'll use enthalpies. I'm going to go ahead and rewrite this, and then I'll have you write it. We'll put a box around it. All right, so I've rewritten the equation, put in the enthalpies, and I've even given us a title here. We have the first law in steady state, neglecting potential and kinetic energy. So go ahead and write that down. We will use it a lot. We'll use it on almost every thermodynamic process. And that's the example that I'm going to do here today. Give you a second to go ahead and get it written down. All right, well, before I go ahead and apply the first law in steady state in rate form, let's talk a little bit about what heat transfer is. Now, whether you've had a heat transfer course before, whether you're in it now, or whether you haven't had it, heat transfer is, the rate of heat transfer is how much energy is crossing the boundary of a system due to a temperature difference. Now, there are a bunch of different kinds of heat transfer. There's conduction, and there's radiation, and there's convection. In most thermodynamic processes, some combination of all three of those are taking place. And so when you do take heat transfer, you'll learn how to calculate heat transfer for all combinations. We use, for the most part, something called the overall heat transfer coefficient to account for the conduction and the convection. But in thermo, we don't need to use those equations. Instead, we find out how much heat transfer there is simply by using this equation. This equation has heat transfer in it, and it's got energies that we can calculate. So rather than having to use conduction, convection, and so on, we'll just use the first law to find our heat transfer. It's getting kind of annoying that that picture keeps freezing on me. So in heat transfer, or excuse me, in thermo, we're always looking at systems. And one system that we can look at is a condenser. So in the Rankine cycle and in the refrigeration cycle, both of which we will look at, there's this thing called a condenser. Now I'm going to draw a simplified condenser. And in my condenser, I bring in some steam. So we have mass, flow rate, steam. And then after it condenses, it goes away and it leaves, and this is called a heat exchanger, mass flow rate of the condensate, C-O-N-D-T. Now if we're in steady state, the mass flow rate of the steam and the mass flow rate of the condensate are the exact same thing. Now how do we get steam to turn into condensate? Well, we have to take energy out of it. Now the way that that's done is by taking some cold water and running pipes through. Wait a minute, now I want it blue. Oh, I guess it isn't going to happen. So I take some cold water and I run it through these pipes. The cold water is inside the pipes and the steam is around the pipe. Hot steam, and cold water. Heat transfers. Heat comes out of the steam and goes into the water. And if you remember the vapor dome, what we would have is we would have water from the vapor side transferring energy out until it's liquid. Well, so what does that mean when we look at the first law? Well, we have to decide what our system is, and I'm going to decide that the system is only my steam. It's only my steam, and it's only my steam while it's in the condenser. So if I go back up, I'm just going to use that same equation up there. Am I putting any heat into my steam? No. Am I doing any work? Well, there are no moving parts here. There are no shafts, no compressors, nothing like that, so there's no work being done. Am I taking heat out of my steam? Yep, taking heat out of the steam. Am I doing work by the steam? Nope. And so very quickly, the equation, all that's left is how much heat is transferred out of the steam, and I'm going to do my algebra here. I'm going to move that to the other side, and it's going to equal the mass flow rate of the steam coming in times the H of the steam coming in minus the mass flow rate of the condensate going out times the H of the condensate going out. And that's it. I've now been able to calculate the heat transfer by only knowing how much mass is flowing through the condenser, and these two will be the same number because it's in steady state, and how much is the H changing from before to after the condenser. So we will do this hundreds of times in a thermodynamic advanced course like power cycles or air conditioners, and it's all about the H. So if you've ever heard people say that, or if you've ever watched the All About the H video, this really is all about the H's. Measuring mass flow rate is quite simple. We just put a flow meter out here, a flow gauge, and measure how many pounds mass per hour are entering or leaving a system. So at a power plant, this is just something you read on a dial. Now, what we haven't done yet is learned how to find the H's, and what it has to do with is the temperature and the pressure and something called the quality. But we will do that in an upcoming video. We will do it together in class. What I wanted to do today was talk about what it means to be in steady state, and then once we have that steady state equation, know that we can manipulate that equation quite a bit to find very simple equations to calculate whatever it is we want. Now notice that what we calculated here was the rate of heat transfer out of the steam. We could have done the exact same thing and said, well, how much heat is being transferred into that cold water? And we would have used that as our system, and we'd use rate of heat transfer in and the H's of the cold water. But when we were done, it would have been the same number, because the rate of heat transfer out of the steam has to equal the rate of heat transfer into the water. That's it for this video on rate of heat transfer and steady state.